against me. And gravity wants to bring me down.
So this week we're going to be talking about gravitational force. And again, it's still a force, so it's still measured in newtons. However, it's one that is caused by gravity, and very specifically of that. And so we'll be looking at some objects and how they relate, going back and forth. So let's say I have two objects here. I have mass 1 and mass 2. These might be two stars, they might be a planet and a moon, something that's significantly large. And we'll talk about those numbers later. And if I have them, there's a certain gravitational force that's created between the two because they both have mass. Anything that has mass has gravitational force. It just takes a lot of mass to actually have anything to do with it. And so if I move these together, it changes the mass, or it changes the force. If I move them apart, it changes the force. And so the relationship between these two is what we're going to be looking at. Now, if instead of having them be of a certain size, if I take out and I make this one a larger one, that will also change the force that goes between them. If it gets closer or farther, it changes the force as well. If I take out this one and I put in another one, and now I have two larger masses, that changes how the force goes. In fact, if I'm adding mass, the force goes up to keep them together. If I'm getting closer, I've got more force keeping them together. If I'm far away, I have less force keeping them together. And so the two pieces that play into this are how big the masses are and how close or far apart they are. We'll look at an equation that goes with that. There's an equation that tells us how much gravitational force is acting between two masses. And it looks like this. We have our masses, and that'll be measured in kilograms. And so we have mass 1 and mass 2. The 1 and 2 are arbitrary. It can be mass 1 and mass 2 and mass 1. It's just showing that there are two different masses that are present in this situation. We have the distance between them, and we'll square that number, and we have our force of gravity that's created. Now we also have this number, this g in the middle, and that's a constant. And what scientists do with a constant is that they take it and they might say, hey, the force of gravity is related to the masses and the distance. We know as the masses go up, the force of gravity goes up. As the distance goes up, the force of gravity goes down to 1 over distance squared. And so the relationship is nice, but by adding a constant, we can make that an equal sign. And we know exactly what will happen depending on what the masses and distance end up being and how that will create our force. And so a constant here is 6.67 times 10 to the negative 11th. And constant, by what it sounds like, is that it does not change. And so every time in every problem when we talk about using g, it ends up being this number. These are the units for it. It's Newton times meters squared over kilograms squared. Anytime we have a constant, it usually has a whole mess of units. Because what you want to do is you're canceling out the units you don't want from these, and you're getting it to the Newton, to what you do want over here. So in this situation, you want newtons because forces are measured in newtons. The meters squared here is on the top of the fraction, and it cancels out the meters squared from the d squared. And then our kilograms squared cancels out the kilograms squared that we have for up top. And so you won't need to reproduce this big mess of units here, but this number you'll need to have in your calculations. And we'll look at that when you look at the calculations. Things to keep in mind with this, there's a few different pieces. First of all, if it has mass, it has gravity. Anything with mass has gravity. Now, you or I, we all have mass, but we're not going to have much gravity between us because this number's teeny, teeny, tiny. You're not going to have, if you just add, a certain kilograms, I don't know, let's say 60 kilograms, cool. 60 times 60 times 10 to the negative 11th, super tiny. So you're not going to have any measurable gravity between people. The other thing is the Earth has a huge amount of gravity. And so if the Earth is one of these masses and you're the other, that's going to overpower anything else that's around. But if it has mass, it has gravity, it just might not be measurable. Second thing to keep in mind is as mass increases, the force of gravity also increases. As distance increases, the force of gravity decreases. The farther away it is, the less effect it can have on another object. So keep these in mind, and you'll do some work with that when you do your lab this week.